Okay, today we're going to look at section 2.7, analyzing graphs of functions and piecewise defined functions. So let's start with test for symmetry. So consider an equation and the variables x and y. Okay, so first up, the graph of the equation is symmetric with respect to the y-axis if substituting negative x for x in the equation results in an equivalent equation. Okay. Next, the graph of the equation is symmetric with respect to the x-axis if substituting negative y for y in the equation results in an equivalent equation. In other words, it's the same equation. And lastly, the graph of the equation is symmetric with respect to the origin if substituting negative x for x and negative y for y in the equation results in an equivalent equation. So let's take a look at a couple of these and see what we've got. So let's look at y equals x squared. So let's see if it's symmetric to respect to the x-axis. We substitute in y for negative, or negative y for y, negative y, x squared. Is that the same thing? No, it is not. So this is not symmetric to the x-axis. We can test to see if it's symmetric to the y-axis. Y equals negative x squared, which is y equals the same as y equals x squared. So it is symmetric with respect to the y-axis. And if we look at the graph of this, x is 0, y is 0, x is 1, y is 1, x is negative 1, y is 1, x is 2, y is 4, negative 2, 4, and you see we have a parabola, and you can see that it's symmetric to the y-axis. Okay, let's look at another one here. What about absolute value of y equals x plus 1? So what happens if we replace x with negative x? Absolute value of y equals negative x plus 1. Not the same thing. What if we replace y with negative y? Absolute value of negative y equals x plus 1. Well, the absolute value of negative y is the same as the absolute value of y. So here we have symmetric with respect to the x-axis. And one more. You have x squared divided by 4 plus y squared divided by 9 equals 1. So let's replace y with negative y, and I get x squared over 4 plus negative y squared over 9 equals 1. And of course, negative y squared is the same as y squared. So we have symmetric to the x-axis. So let's test the y-axis. Place x with negative x and square it. 4 plus y squared over 9 equals 1. That is simply x squared over 4 plus y squared over 9 equals 1, which is the same. So we have symmetry to the y-axis. Now let's check them both. Negative x squared over 4 plus negative y squared over 9 equals 1. Well, as we've determined, that's x squared plus 4. That's y squared plus 9. So this is symmetric through all three. Next up, an even or odd function. Even and odd functions. So, a function f is an even function if f of negative x is equal to f of x. For all x in the domain of f. Essentially, it's symmetric with respect to the y-axis. Okay? So essentially, if it is symmetric with respect to the y-axis, it is an odd function. or an even function. A function f is an odd function if f of negative x equals negative f of x. Again, for all x in the domain of f. So essentially, an odd function is symmetric with respect to the origin. So let's look at some equations here. Start with m of x equals negative x to the fifth plus x to the third. So it's always a good idea to check to see if it's even first. So we want to find out if f of negative x is equal to f of x, or in this case, m of x. So what is m of negative x? Well, it is the negative of negative x to the fifth plus negative x to the third. Okay? So we're taking the negative, and negative x to the fifth is simply the negative of x to the fifth. And this is simply minus x to the third. So as you can see, this is not the same thing as this. This and this are not the same thing. So it is not even. So next, let's check to see if it's odd, in which case we want to show that f of negative x, which is what I have here, is equal to negative f of x. So what is negative m of x? Well, I just take negative. Okay. So this is what? The negative of negative x to the fifth minus x to the third. Same thing. So this function is odd. Let's look at another one here. So let's say g of x equals 2x to the fourth plus 3x squared. So let's test to see if it's even. So we'll find out what g of negative x is. Well, that's 2 of negative x to the fourth plus 3 of negative x squared. So 2 negative x to the fourth is the same as x to the fourth plus 3, and negative x squared is the same as x squared. And thus we have the same thing. This one is even. Let's do one more. And we'll go with h of x is equal to 2x to the third plus x squared minus x. So let's see if it's even. What is h of negative x? 2 times negative x to the third plus negative x squared minus negative x. So this is 2, and this becomes negative x to the third. This becomes plus x squared, and this becomes plus x. So this and this are not the same, so it is not even. We'll check odd. We're going to find a negative of h of x. That's the negative of 2x to the third plus x squared minus x. So this is simply negative 2x to the third minus x squared plus x. Are these the same? They are not. So, a little handy trick. Look at the exponents. All the exponents in this were odd. It's odd. All the exponents of this were even. It's even. This had a mixture of even and odd exponents, so it is neither. So that's a little helpful hint. Okay, so now we come to piecewise functions. Now let's look at an example and we're going to graph these. F of x is equal to x plus 7 for x less than negative 2, x squared or negative 2 less than equal to x less than 1, and 3 or x greater than or equal to 1. So this is going to be a function in 3 parts. So here's the trick. We start here with this. So we're looking at x plus 7 or x less than negative 2. So we'll start with negative 2. Now, this is just strictly less than, so we won't include this point. So if x is negative 2, this becomes negative 2 plus 7, which is 5. So we go up here. Now this point is not included, so we use an open circle. Now to complete this graph, we keep going less than negative 2. So let's go with negative 3. What do we end up with? 4. And we'll go negative 4, 3. So essentially, that is this part of the graph. Okay, now it's simply x squared for x equals negative 2. So what's negative 2 squared? 4. Right there, and it is included. Okay, then we have negative 1 we can use. What's negative 1 squared? 1. Then we have 0. 0 squared is 0. Then we have 1, and 1 squared is 1. But it's not. It's strictly less than, so we use a dot again. And this is like this. Okay, then our third part here is for x equals 1, we go to 3. For x equals anything above 1, we go to 3. So that is our 3 parts. Notice at x equals negative 2, here I have an open circle, here I have a closed circle. So there's only one y value for x equals negative 2. Same thing here at x equals 1. That's why we can call this a function. Okay. So let's look at an application of this. So we have a retail store buys t-shirts from a manufacturer. Cost is $7.99 per shirt for 1 to 100. And that's inclusive. Then the price is decreased to $6.99 per shirt thereafter. So we're going to let for greater than 100. So we're going to let, no, we'll just let X equal number of shirts. And our cost, C of X, is going to equal $7.99 times X for 1 less than or equal to X less than or equal to 100. That covers this. It was inclusive, so, and then $6.99 times X for X greater than 100. And there we go. Oh, we wanted total cost, so this will actually be 100 times 799 or 799 plus 699 times X minus 100. Or X greater than 100. So what we're looking at here is we sold 100 shirts, so we have $799. Then for every shirt over 100, we're charged $6.99. So whatever X is, 150, we subtract 100 from that because the first 100 are right here. So then we get 50 times $6.99. And that's how that works. Okay, so now next up is intervals of increasing, decreasing, and constant behavior. So we start with suppose I is an interval contained within the domain of F. So we're going to start with F is increasing on I if F of X1 is less than F of X2 or all X1 less than X2. Then F is decreasing on I if F of X1 is greater than F of X2 for all X1 greater than X2. And lastly, F is constant on I if F of X1 equals F of X2 for all X1 and X2 on I. So what does this mean? Essentially, looking at it, increasing. I look at it this way. As X increases, Y increases. Okay? For every X1 less than X2, f of X1 is less than X2. See, we're constantly increasing. Decreasing. As X increases, Y decreases. And constant, as X increases, Y is constant. So essentially, look at what Y is doing as X increases. If Y is increasing, then it's an increasing function. If Y is decreasing, it's decreasing. If Y is staying the same, it's constant. So let's look at a graph. See if I can draw this. And this probably won't be accurate, but I'll label my points. -5, -3. Then I go up like this. Then I go over like this. Then I go up like that. Then I go down. Okay, so this point here is -3, 1. This point here is -1, 1. And this point here is 2, 3. So using interval notation, when is this increasing, decreasing, and constant? So I start here at -5. My X is increasing. What's my Y doing? It's increasing as well. So from -5 to -3, I am increasing. When we do these intervals, we use the X values. Now here I am at X equals -3. I'm increasing my X to -1. And what's happening there? It's staying constant. So from -3 to -1, it's constant. Okay, now I'm here at X equals -1. I'm going up to X equals 2. As my X increases, my Y increases. So I'm increasing here as well from -1 to 2. Again, we're putting the X values in here. And then from -2 or from 2 all the way to infinity, 2 to infinity, I'm decreasing. Now, typically, we use parentheses because you don't include the endpoints because at an individual point, it's not doing anything. It's not increasing, decreasing, or anything. Next, we look at relative minima and relative maximum. So let's see. For f of a, or f of a is a relative maximum of f if there exists an open interval containing A such that f of A is greater than or equal to f of x for all x in the interval. We'll look at an example of this and it'll make a little more sense. Also, f of b is a relative minimum of f if there exists on, or if there exists an open interval containing b such that f of b is less than or equal to f of x for all x in the interval. We define an open interval as an interval in which the endpoints are not included. We'll go more into what that means in calculus. So let's look at a graph here. And we're just going to go something like this, like this. And we'll label this -3, -3. And this I'll label 1, 1. And this I'll label 4, -3. So essentially what we're looking at, we're looking for a relative minimum, a relative maximum. So we're looking for a point. So let's start with a maximum. Maximum is a high point. So anything over here, this goes on forever. So I can't really use any of these points. Same here, this goes on forever. However, I do have a little uptick here. So I have a relative maximum at 1, 1, right here. Now, in this case, I have two relative minimums down here at -3, -3, and 4, -3. Okay. So let's look at y equals x cubed minus 4x squared plus 3x. So we're going to put this in our calculator. So you want to hit y equals, and to punch this in, hit x to the third minus 4x squared plus 3x. Remembering that x is that button that says x t theta n. So punch this into your calculator. X to the third minus 4x squared plus 3x. Then hit graph. Okay, we're going to get a shape that looks something like this. So it looks like I have a maximum here and a minimum here. So I can find these with my calculator. I can hit second and trace. This will give me the calculate menu. I want to find, well, let's find this point here. So I want to find a maximum. Maximum. That's number 4 on my calculator. So go down to maximum, hit enter. Now, what you have to do, you'll note in the bottom left-hand corner, it's going to say left bound. So this is the point I'm trying to figure out what it is. So I need to pick a point somewhere in this area to the left of that point. I move my arrows till I'm there, and I hit enter. Now in the bottom left corner, it says right bound. So now I need to find a point somewhere in here that's to the right of my maximum. So hit my arrow key, go around and over, and hit enter again, and then hit enter a third time, and we should get x equals 0.48 or 45, sorry. Point 0.451414 and so on, and it should say y equals 0.631130. So that's how we find our maximum. Now we need to find our minimum as well. So again, hit second, trace. Minimum is number 3. Now again, we want to be to the left of it first. So here's a point to the left of it. Hit enter. Then it says right bound. So go over here and hit enter, and then hit enter a third time. So here's my max. And my min is 2.21524. That's my x value, and my y value is negative 2.1126. Now, one of my issues with using the calculator for this, we usually say around the 2 decimal places because the different calculators can be slightly off when we get further on. Mine actually has 2 more decimal places. So this would be my maximum. I would put 0.45, 0.63, and my minimum, I would put 2.22 and negative 2.11. And again, you need to practice these because this will help you later on. Okay, so that's it for this section. Have a good day, and I will see you next time.